Hey guys, so today we'll be looking at the hill climbing heuristic. It's one of the heuristics listed in your outcome for VC algorithmics, and it goes alongside simulated annealing and a couple other heuristics. So what is the hill climbing heuristic? In essence, you plot each of your variables or features you'd like to tweak in a problem space, such as the GIF on the right, where you can see each axis is a different feature. Then you start somewhere arbitrary on that space. So once you've started at that spot, you then check how efficient it is with an evaluation algorithm, as pointed out with the yellow arrow. And then you check each of your neighboring options from that point. So each neighboring option will have a different change in a feature. So depending on the axes, you might tweak this parameter a little bit or tweak that parameter. And then you check the efficiency or the evaluation of each spot of all your neighbors. And then you pick the highest neighbor. So out of all those neighbors, you move to the highest evaluated efficiency neighbor, and then you repeat those steps and check each of those neighbors. So here's an abstracted example. We've got two images here. The top one and bottom one are the same. One of them is just a contour view. So for the example, I'll show the top image as what the algorithm sees and the bottom as the entire problem space already solved. So as you can see here, when we start off with the hill climbing algorithm, we have this fog of war that the algorithm can't see. It hasn't solved the efficiency of all of those spots. We can only see what's in that circle. So the red spot is where we've started, and the green spots are the neighbors. And with each of those neighbors, we'll check the efficiency or evaluation of each of those spots, then we'll move to the highest one. So you can see that we've moved up the hill because it had a higher efficiency, an abstracted efficiency, and then we repeat those steps until we've reached a maximum efficiency. So you can see here we've moved again, just straight up. And then once we're at the top, our neighbors are either less than or equal to an efficiency of that spot. So we can't really move anywhere. What's happened is we've gotten stuck at a local maximum. So that means that no matter where you are in that local maximum, all your neighbors are less than or equal to, and you can't improve anymore. So the nature of this algorithm says that it will get stuck at local maximums and it won't reach the global maximum by itself. So you can see in our problem space, there is another spot that is much better than where we currently are. But to the rules of the algorithm, we can't go there. So the only way to get over to that spot would be to kind of shift over to that purple arrow there. And that's done using another heuristic called simulated annealing, which allows the algorithm to move to another spot that's potentially worse, but we can see that it can lead to a better example anyway. But that will be covered in the simulated annealing video.
So when do we use the hill climbing heuristic?
When you have parameters to optimize in a problem that's resourceful or complex to run. So for example, in most optimization problems, such as the traveling salesman problem, you would use the hill climbing algorithm. And you wouldn't use it in something simple like calculating the temperature or max temperature over a 3D surface. So you can see that can still be modeled in a 3D hill, but getting to the top is a lot simpler, and there's no need to optimize any parameters because you can just solve it mathematically or something similar like that. So some examples of applying this algorithm are, as said, the traveling salesman problem, where instead of using numerical features, you use combinatorial features, like one axis would be a series of steps and the other would be a series of steps in a different way. And you could use it to find a good picnic spot. You can have your X and Y axes as the physical location, but your evaluation algorithm can use parameters from another part of the model rather than just where you are, such as the shade, sun, or if there's any prickles there. Same thing with camera settings, and same thing with House MD, actually.
If the blood vessels are inflamed, that's going to look exactly like what we saw in the MRI from Trenton County. The pressure's going to cause neurological symptoms.
Can't diagnose that without a biopsy.
Yes, we can. We treated her. If she gets better, we know we're right.
And if we're wrong?
We learn something else.
So if you've ever seen the show, he gets stuck at local maxima sometimes where he thinks he's seeing an improvement, but all of a sudden, he hasn't really solved the problem. He's just gotten to a local maximum where he can't go anywhere. So digging into the House MD example, we kind of need to change our evaluation to make it more computable. So for this example, we'll just leave the evaluation algorithm as, did the patient get better? Because we can't try multiple things on the same sick patient and try again. So we'll start where the patient is just sick, their feeling is 0 out of 10, and then we'll try some methods and evaluate them. So starting this method, we'll call it method 3. The patient feels a 6 out of 10. So that's one of our neighbors. We'll try the other neighbors. Method 2, they're feeling a 4 out of 10, so not as good as 3. Then method 1, they're filling a 9 out of 10. So that's our highest neighbor. That's looking very efficient. We'll go in that direction. So now we're on the 9 out of 10 node. We'll try the next method that follows that, which is the 1.1 neighbor. And the algorithm would check the method 1 neighbor or its surrounding neighbors as well. But for this one, we'll try method 1.1, which is an 8 out of 10. So that's not an improvement from 9 out of 10, and we're stuck at a local maxima. So there's nothing we can do. So as said, we need to do some simulated annealing and shift around to get that to work. So we'll try another neighbor that was seemingly worse, which is a 4 out of 10. And then when we explore the neighbors of 4 out of 10, we see that there was a 10 out of 10 option next to that as well. So then we would have reached the global maxima and our problem is solved. On that as well, you don't always know what the best value is or the most optimal spot is. You don't always know your global maximum. This is common in NP hard problems, such as the traveling salesman problem, where you don't know the shortest route until you've figured out every single route. To summarize, the constraints while you're solving is that you can't see more than one step ahead and you can't remember where you've been. So that ties into the main point that you can't backtrack and you don't remember the previous positions. You can see that as a limitation. And you can apply this on different ADTs or models, such as arrays, lists, or graphs. And each axis or dimension is a feature in your problem. So one axis can be the efficacy of your combinations of variables, such as your Z as that first GIF showed. And then you can apply that back to an example with the picnic spot, where X and Y are locations on a field, and Z is how good that spot is for the picnic. Tying this into VCE algorithmics, it's part of outcome 2, where you need to know how to use the hill climbing heuristic to solve problems, explain why it's good, explain why it's bad, just a general overview of the hill climbing heuristic. And this really pairs well with the simulated annealing heuristic as mentioned, but that will be done in another video. So thanks for watching.
Are you guessing?
Yes.
Too bad, you're right.